Okay, so this is 351. So it says a toy rocket is launched with an initial velocity of 12 meters per second in the horizontal direction from the roof of a 30-meter tall building. So here is the building. Here's the initial velocity. It's horizontal. Now, in terms of vectors, what it's saying is that V0x, actually just V0, the initial velocity, is equal to 12.0 meters per second I plus 0 meters per second J. Okay, so that's the initial velocity. The initial displacement, or the initial, so that's the initial velocity vector. The initial position vector is equal, what we're going to do is you have to define where 0 is. So I'm going to define 0 here at the base of the building. So the initial x displacement is 0. So you get 0 meters I plus, and it's a 30-meter tall building, so you get 30.0 meters J. So that's my initial position vector. You can kind of think of it as this is the vector here, the position vector. And this is my velocity vector. Okay. Now, it says the rocket engine produces a horizontal acceleration of such and such. And so what you have in this case is you have the acceleration vector as a function of t is going to be equal to 1.60 meters per second cubed times t times I hat minus 9.8 meters per second squared J hat. So it says that the y component of acceleration is negative 9.8 meters per second squared, and the x component is 1.6 meters per second cubed t times I. So that's the acceleration vector. Ignore air resistance, so that means we just don't, means this is the total acceleration. What is the horizontal, at what horizontal distance does the rocket travel before reaching the ground? Okay, so how do we figure this one out? Well, what we need to do is we need to integrate this to get velocity, and then integrate velocity to get position, and then all we have to do is the solution is when the y component of the displacement is 0. So the velocity vector as a function of time is the integral of the acceleration vector with respect to time times dt. So what we do is we plug in the acceleration vector So that's my acceleration vector times dt. So we integrate those, and you do them separately. So the integral of t dt is t squared over 2. So the first term is going to be this divided by 2. So I get 0.8 meters per second cubed t squared I hat minus the integral of dt is just t, so I get 9.8 meters per second squared t j hat plus my arbitrary constant vector. So that's one difference, is when you're dealing with vector, so you have a vector arbitrary constant. So now what we do is use the initial conditions. So the initial conditions here for velocity were this. So let's bring that over. And then use that to solve for the arbitrary constant vector. So this is the velocity. That's the left-hand side, 12.0 meters per second. I minus 0.0 meters per second J is equal to, so then what we do is just plug in T equals 0 into here. So that just gives you 0I plus 0J plus my arbitrary constant vector. So my arbitrary constant vector is just equal to 12.0 meters per second I plus 0J. I'm just going to leave that out because it's 0. Okay, so that's my arbitrary constant vector. So my velocity vector with the arbitrary constant now specified is 0.80 meters per second cubed T squared I hat minus 9.8 meters per second squared times J hat plus 12.0 meters per second I hat. And I can combine these two together, so I get my velocity vector as a function of time is 0.80 meters per second cubed T squared plus 12.0 meters per second, whole thing times the unit vector in the I direction, minus 9.8 meters per second squared. And I think I forgot something here. Hold on just a second. Yeah, that was supposed to be a T right there. Okay. And okay, so that works out. So just gonna put, I'm gonna put a T right here. T J. Okay. So that's my velocity vector. Now the displacement vector, which I'm going to use R, not X, R of t is the integral of the velocity vector times dt. So I take my velocity vector, which is 0.80 meters per second cubed t squared plus 12.0 meters per second times I minus 9.8 meters per second squared t times j hat, the whole thing times dt. So I integrate that. So the integral of 0.8 meters per second cubed t squared is going to be 0.80 over 3, because I'll get t cubed over 3. So I get t cubed. Let me make sure I put my units in here. So the units are still meters per second cubed, t cubed, plus when I integrate dt here, I'll get 12 meters per second times t, and that whole thing will be multiplied by my I vector. And this, now when I integrate the y part, the integral of t is t squared over 2, so I'm going to take 9.8 and I'm going to divide by 2, which is 4.9 meters per second squared times t squared, whole thing times j hat, plus my arbitrary constant vector, which again is different for my second case. when I'm talking about displacement or displacement vector. Okay, so we take t, integral to t dt is t squared over 2, so I divide 9.8 by 2, I get that. Okay, now I have to use the initial condition for the displacement, so it's this one right here. So that's my initial displacement vector. So that's the displacement vector at t equals 0. And if I plug t equals 0 in here, you can see everything goes to 0. So that's going to be my arbitrary constant vector. Since you get 0 here, 0 there, 0 there. So my displacement vector, as a function of time, ends up being 0.80 divided by 3 meters per second cubed, t cubed, plus 12.0 meters per second t, whole thing times I hat, minus 4.9 meters per second squared t squared, but I'm going to put the minus sign with that. So I'm going to put a plus and then I'm going to put a minus there. And then what you have is plus 30.0 meters, the whole thing times j hat. So that's my position vector as a function of time. So you can see at t equals 0, you get 30 meters. Now the question is, what they're asking in this problem is, what horizontal distance does the rocket travel before reaching the ground? So to do that, we're going to use when does r sub y equal 0 meters. So you got to figure out what time does this go to 0. So the question is, if you take the y component and you set that equal to 0. So I'm just taking the term in the parentheses. So we'll get t squared is equal to 30 meters divided by 4.9 meters per second squared. So what I've done is I've moved this to the other side, divided by negative 4.9. The negatives can't, well, it'll become positive, divided by 4.9. And you get t squared is equal to 30 divided by 4.9, which is 6.12 seconds squared. And therefore t is the square root of that, which is 2.47 seconds. Okay, so that's the time it takes for the y component of the position vector to 0. Then you plug that into this expression to find the x component. So I need to take this whole thing here, and I don't know why that does that. Okay, let's just clone it. I'll drag it over here. So this is so what I'm looking for now is I want to find out what is r sub x at t equals 2.47 seconds. So all I do is take the x component. So r sub x is going to be equal to 0.80 divided by 3 meters per second cubed times 2.47 seconds, quantity cubed, plus 12.0 meters per second times t, which is 2.47 seconds, and that's going to give me a number. And notice the units work out to be meters. 0.8 divided by 3 times 2.47 cubed plus 12 times 2.47, and I get 33.7 meters is the answer. And if I look at the answer, I get 33.7 meters. Awesome. So that's how you do it vector-wise. So let's kind of review what we just did here. If you're confused, I guess you can go back and watch the whole thing again. But what we did is we said the acceleration, it had an x component of acceleration, a y component of acceleration. To get the velocity vector, you integrate the acceleration vector. So this is the acceleration vector. You integrate each component separately. So this is the velocity vector with this arbitrary constant vector. You use the initial velocity vector to find the arbitrary constant vector, and then that'll give you pretty much a particular solution for the velocity as a function of time. So that's the whole thing. Then you integrate that vector to get the position vector. So we integrate it again, integrate each term separately, keeping your I and j components. Then you use the initial condition for the displacement vector. Find your arbitrary constant vector for this integration. So you get your final position vector here as a function of time. And I said that it hit the ground when the y position went to 0. So I set r sub y, which is this part, equal to 0. Found the time equals 2.47 seconds when that happens, and then you plug that into your x component to find out how far it moves in the x direction. And we did that. We got 33.7 meters.